Swayam Prabha. Digital India. Educated India.
So, now like I said, the steady state quantities will be constant, that is the voltage across the capacitor will be constant, current through the inductor will be constant. Now, this is true even for arbitrarily complicated circuits. So, if the current through inductor is a constant, then the voltage across the inductor is 0. If the voltage across the capacitor is a constant, the current through the capacitor is 0. Okay. So, just like before, for the first order case, you evaluate steady state with constant inputs. This is what is important, constant inputs. To evaluate this, you short circuit the capacitors and open circuit the shorts, I said it backwards, sorry about that. You short circuit the inductors and open circuit the capacitors. Okay. So, if you do that for this particular circuit, what will we get? What is the value of steady state Vc? You please use this algorithm and find the steady state Vc. What is it going to be? So, clearly it will be the input source itself, because we have Vs which changes from 0 to Vp, and I have short circuited the inductor. Okay, that is the inductor short circuited and the capacitor is open circuited. So, if you have Vp here, exactly the same thing will appear there. Okay. So, Vc of infinity will be Vp. Okay. Is this fine? So, a part of the response can be evaluated very easily. Okay. So, now let me give another example so that you clearly understand what is going on. So, let me take the other circuit. Let me say that Vs again changes from 0 to Vp, and I have RLC, and in this case I am interested in the inductor current. Okay, that is my variable of interest. I know that IL will also be of the form of steady state response plus transient response. So, what is the steady state response of IL in this particular circuit? So, I got two different answers. Let us see which is correct. Or I will short circuit the inductor and open circuit the capacitor. So, if I have Vp, which is the constant voltage Vs after t equal to 0, the current that flows this way would be Vp by R. So, the steady state value of IL is clearly Vp divided by R. Okay. So, this is how you can find the steady state response, quite easy. Open circuit the capacitors, short circuit the inductors and find the corresponding values. Okay. So, next thing we have to do is calculate the rest of it, which is a little more complicated, but certainly possible. Okay. So, again I will make analogies to the first order circuit and go with it. So, now our goal is to find the transient response or the natural response. Okay. So, let me write it down for the first order case again. Now, we know the exact solution for this, okay. But let me do it in a slightly different way now. The differential equation governing Vc is Rc dVc by dt plus Vc equals something. Okay. Now, to evaluate the kind of natural response, I do not need the right hand side. I could also set this to 0, because even with 0 input I will have some natural response. Okay. Now, for a particular input you have to find the natural response, that we will do by adjusting the initial condition. Okay. I will explain exactly what I mean by that. Now, we know that the natural response for this differential equation will be of the form exponential some exponential, okay, and let me call it exponential p times t. Okay. Let me call it exponential p times t. Remember, we know exactly what the answer is. It is exponential minus t by Rc. I am trying to get the same answer in a slightly different way. Okay. Now, we know that, like for instance, I could rewrite this and say that the time derivative is minus 1 by Rc times Vc. This we did earlier. What it means is that the time derivative is a scaled version of the function itself. Okay. And we know that that property is true if the function is an exponential. If the function is an exponential, the time derivative is also an exponential, but it could have some scaling factor. Okay. So, we know that exponential will satisfy this. We just have to find the constant inside the exponential. Okay. Now, how do we find the constant? Now, for this we have already found it, but I will do it in a more general way, which will also be useful for second order circuits. So, what I do is I will assume that it is exponential of p times t. Okay. So, what will I get? I will have Rc, the time derivative will be p times exponential of p times t plus Vc, which is exponential of p times t equals 0. And this exponential pt is common to the two parts, and that will be that can cancel out. Okay. So, what I have will be Rc times p plus 1 equal to 0, or p equals minus 1 by Rc. Okay. So, this is an alternative way of finding the argument of the exponential. Okay. Now, we did it earlier, we already know the answer. Now, we know that this answer is correct, because if I substitute this into that one, what I get will be that thing. Okay. So, now we can use the same method for second order equations, it turns out. Okay. So, this equation from which we get the value of p is known as the characteristic equation. Now, remember, we got this by substituting V c equals exponential p t. Okay. Now, we do not have to do it every time. We know that if you have a first derivative, you will have p, and if you have V c, you will not have anything, and exponential p t will be common to every term, and that will cancel out. Okay. This will become even more clear when I do the second order case. So, all we have to do is, wherever I see a first derivative, I put p, and wherever I see the function, I just have 1. Okay. So, then I will get the characteristic equation. Is this clear? Any questions? And solving this, what we get are characteristic frequency. In this case, frequency. In a higher order circuit, it will be frequencies. And what is this? This is nothing but the reciprocal of the time constant, okay, or rather negative reciprocal of the time constant. Any questions about this? Okay, there is a question of how does this p come about. See, I know that if the differential equation is of this type, that is dVc by dt is proportional to Vc, okay, basically this differential equation, I know that an exponential will satisfy it, okay, because what this is saying is the differential coefficient, the derivative, is the same as the function with some scaling factor, okay. Now, you know from basic differentiation that if you have an exponential, its derivative will also be an exponential with some scaling factor. So, I know that the form of Vc is exponential of time. Of course, there can be a constant here. So, that constant I have assumed to be p. Okay, I have to find out what p is for this particular circuit, but I have assumed that the solution is of the form exponential pt. Okay, and I substitute it here. I get RC times p times exponential pt plus exponential pt equal to 0. Okay. So, this is a standard way of solving differential equations, okay, because I know exponential pt can be a solution. I do not know the value of p, I will substitute that and then find the value of p. Okay. Is this fine? You also know that the value of p we found is minus 1 by RC. If I substitute it there, I will get exponential minus t by RC, which is consistent with what I had earlier. These things we had already determined earlier. Is this okay? Whatever appears in the exponential as t by something, that is the time constant by definition, okay, because we have seen that if you have exponential t by tau, the amount of time it takes for it to settle is related to this tau, okay. So, now I will do the same for a second order circuit. Okay, and Vs changes from 0 to Vp, and I am interested in Vc. Okay. So, now the differential equation for this is LC d square Vt by dt square plus RC dVc dt plus Vc equals something. To find the natural response, I will simply set the right hand side to 0. Okay. Then I will get the form of the natural response. The coefficient of the natural response I will determine from initial conditions. Okay. So, again in this case also exponential will satisfy it. So, I will assume that Vc of t is exponential Pt. Okay. So, please substitute this here and find the characteristic equation. Please try this out. Please assume that Vc of t is exponential Pt and find the characteristic equation. Locked. So, I have an answer here which is correct. So, all we have to do is substitute this. What I have would be exponential Pt in place of Vc plus Rc times P exponential Pt, okay, because this will be that one, this will be that one, and if I differentiate it once more, I will get P square. Okay. So, I will have LC P square exponential Pt. Okay. This corresponds to this one, and the right hand side is 0, and by cancelling this exponential Pt, I will get LC P square plus Rc times P plus 1 equals 0. Alternatively, it could also be written as P square plus R by L times P plus 1 over LC equals 0. Okay. This is the characteristic equation. I hope all of you are able to derive this yourselves. All we have to do is to substitute Vc is exponential Pt in this equation. Okay. Any questions? Okay. Now, from this we can solve for the characteristic frequencies or equivalently characteristic time constants, but as I mentioned earlier, for higher orders than 1, it is common to speak of characteristic frequencies P rather than characteristic time constants. But if you want to call them time constants, that is okay, then the reciprocal of P will be the time constant. Okay. So, now clearly there will be two possible solutions for P, and also the nature of solution will be different depending on the values of the coefficients. Okay. So, this is the characteristic equation of a series RLC circuit. As I have been emphasizing, I have taken Vc as an example of the quantity of interest, but you take a series RLC circuit. By that I mean, if you null the independent sources, you get a series RLC, and then you pick any variable of interest, okay, the inductor current, capacitor voltage, whatever it is. Then you will get the same characteristic equation, okay, because the left hand side of the differential equation will remain the same. So, for any series RLC circuit, wherever you apply the source or whichever variable you calculate the differential equation for, the characteristic equation will remain exactly the same, okay, and that is P square plus R by L times P plus 1 by LC equals 0. So, this has two solutions. Okay. Now, there are the two solution would be in general. I think all of you know the formula for solution of a quadratic equation. It will be minus R by 2L plus square root of okay. So, this is the solution in general. Okay. Now, this can give you three different kinds of solutions. The two characteristic frequencies P1 and P2 could be real and distinct. What is the condition for the characteristic frequencies to be real and distinct? Please give me the answer. When will P1 and P2 be real and distinct? See, you know that solutions to a quadratic equation can be, I mean, you will always have two solutions, but the two solutions could be real and different from each other. The two solutions could be real and the same as each other, and also the two solutions could be complex conjugates of each other. My question is, when are the two roots, when are the two characteristic frequencies real and distinct, that is real and different from each other? I think the question is not very clear, or somehow you have not understood the question properly. We will have two values of P1 and two values of P. Okay. That is P1 and P2. Okay. The two values of P are given by P1 and P2 by these two solutions, minus r by 2l plus half of square root of this, minus r by 2l minus half square root of this whole thing. Okay. This is just the solution to this quadratic equation, that is all. Okay. Now, why am I calculating the solution to this? If you recall here, I have a first order equation in P, I solve that for P and I will get the characteristic frequency. I have to put this into exponential. Here I have a second order equation for P, so I will get the characteristic frequencies, two of them, and I have to put them into two exponentials. Clearly there will be two exponentials which will satisfy this. Okay. So, please tell me, when will the two values P1 and P2 be identical to each other? Okay. Clearly there are two values, one when this is plus, one when this is minus. Okay. So, my question is, when is it that the values of P1 and P2 be identical to each other?